Good evening. I was just made aware that my video for 5.1 that I posted earlier did not have any volume, and I'm sorry, so here I am re-recording this. Have no idea what I said before, but we're teaching out of the same textbook and it's the same note set, so it should all be the same. So the derivative of a function is associated with rates of change and slopes of tangent lines. We also know that antiderivatives reverse the derivative operation. So here's a question. What is the geometric meaning of the integral? And some other fun things to remember is that the derivative of position is velocity, and the derivative of velocity is acceleration. So obviously derivatives are related, have a physical and a geometric meaning, but we're interested in what is the geometric meaning of the antiderivative or the integral. So imagine you have a car that's traveling at a constant velocity of 60 miles an hour along a straight highway over a 2-hour period. The graph of the velocity function v equals 60 on the interval 0 to 2 is a straight line, and we have that right here. The displacement of the car between t equals 0 and t equals 2 is found by a familiar formula. Displacement equals the rate you traveled times the elapsed time. So we traveled at a rate of 60 miles an hour, and we were traveling for 2 hours. So 60 times 2 is 120. We traveled 120 miles. And as it turns out, that 120 is exactly the area underneath the curve of our velocity function. So all this area shaded in green adds up to be 120 miles when we think about it. And that's simply from taking 2 hours being my elapsed time times velocity, which is 60 miles an hour. We just get the area under the curve of a rectangle. So here in this example, we're going to take the velocity to not be a straight line. Instead, we're going to take the velocity to be v equals t squared, where our time interval goes from 0 to 8. And I want to approximate the displacement of the object by dividing the time interval 0 to 8 into n many subintervals of equal length. On each subinterval, approximate the velocity with a constant equal to the value of v evaluated at the midpoint of the subinterval. And I want to do this for n equals 2, n equals 4, and n equals 8 subintervals of equal length. So the first thing we're going to do is divide into 2 equal subintervals. So I divided 8 by 2 and I get 4. So once every 4 seconds I have a new interval. So it looks something like this: 1 interval, 2 intervals, and we're going for the midpoint. So the midpoint of 0 to 4 is 2. Let's see, 0 to 4, and then we have 4 to 8. My midpoint here is 2, and my midpoint here is 6. So what I'm going to do is I want to calculate the height and the width of this rectangle. I already know that my width is 4, but I want to know the height, and we said the height is going to happen at the midpoint. So when t equals 2, we want to measure that. When t equals 2, we want to measure that. V equals t squared. Two times 2 equals 4. Now that is going to be the rate at which we traveled, so meters per second. And we want to know, and we know the we know the width, which is 4 seconds. So we get 16 meters is what we traveled in. That's the area of this very first red block. For the second one, we need v of 6 equals 6 squared equals 36 meters per second times 4 seconds equals 144 meters traveled. So the total area of both of these rectangles is going to be 16 plus 144 equals 160 meters. So that's our very first approximation. And the second approximation we're going to do with 4 rectangles, because as you can see, using these 2 rectangles to measure the area between this curve going from here to here and here it misses out on what's going on here and what's going on here, but it says that we have something going on here and something going on here, which just isn't true. So maybe there's a better fit, and in fact, when we use 4 subintervals, we can see that we have that. So the next step is to divide into 4 subintervals. 8 divided by 4 is 2, so 0 to 2, 2 to 4, 4 to 6, 6 to 8. And we get our subinterval 1, 3, 5, 7. And now we can set up our equation. So 1 squared is 1 times 2, which is our width, plus 3 squared is 9 times 2, plus 5 squared is 25 times 2, plus 7 squared, which is 49 times 2. And all of this adds up to be 168 meters. So this one is a better fit, and it's saying that, well, we've got more area under this curve than we thought we had initially. So these portions are going to be overestimates, saying we have more area than we thought we did, whereas these areas are saying, hey, we're not accounting for some area. So 168 is getting close, but it's not quite there yet. So what if we use 8 subintervals and we have something that looks like this? Obviously, this is going to be a better fit because we're using more subintervals. So this is going to have less of those overestimates and fewer of the underestimates. So for this one, I'm going to let you guys do the math on this, and I'm just going to give you the final answer. When we have 8 subintervals, the length of each subinterval is 1 second, and we end up with an answer of 170.0 meters traveled. So we wouldn't spend so much time investigating area under curves if the idea only applied to computing displacements from velocity curves. However, the problem of finding area under curves arises frequently and turns out to be immensely important, as you'll see in the next 2 chapters. For this reason, we now develop a systematic method for approximating area under curves. Consider a function f, which I have drawn here, that is continuous and non-negative. That means it never dips below this x-axis. And when I'm drawing it, I never pick up my pencil. It's continuous and non-negative between A and B. The goal is to approximate the area of the region R bounded by the graph F and the x-axis from x equals A to x equals B. We begin by dividing the interval a to b into n many subintervals of equal length, where x equals 0 equals a, and xn equals b. So x0 to x1 is a to x1. Then we have x1 to x2, on and on until we have xn minus 1 all the way to b. And the length of each subinterval, denoted delta x, is found by dividing the length of the entire interval by n. So if I have 6 subintervals, then I use n equals 6. So delta x equals b, my endpoint, minus a, my starting point, all over n, which is the number of intervals. The endpoints x0, x1, x2, all the way to xn minus 1 and xn of the subintervals are called grid points, and they create a regular partition of the interval a to b. And you can see that the distance between each set of grid points is exactly the same, so we can use the exact same number. The kth subinterval, so if we just pick a random one in the middle, x minus k minus 1 to xk, and we choose any point within this subinterval, xk star, and build a rectangle who is the function evaluated at xk star, the area of the rectangle on the kth subinterval is height times base, otherwise known as f evaluated at xk star, that gives us our height, and our width, which is delta x, where k equals 1, 2, all the way up to n. So that's how we do it in general, and then we go ahead and we just add all those pieces up. Summing the areas of the rectangles that we have drawn, we obtain an approximation to the area of R, which we call a Riemann sum, and it's RIEMANN but it's Riemann with a hard E sound, and it's because he's German. So we should have, when we add up all these little rectangles, we should have some dot, dot, dots there. Sorry, that kind of looks like a chicken to me. But we have the height of the first rectangle times the width of the first rectangle, plus the height of the second rectangle times the width of the second rectangle, on and on till we get to the height of the last rectangle times the width of the last rectangle. And the three notable Riemann sums are the left, right, and midpoint Riemann sums, and we'll get into those in just a second. So here we have a left Riemann sum, and it is kind of blurry, but I definitely grabbed this image straight out of your textbook instead of making it myself. But here, when we have our regular partitions, so I'm going to go ahead and subdivide these up. Each length is delta x, and when I choose my xk star, instead of choosing some random point in between one of my grid points, I choose the leftmost grid point. And that's where I decide to draw my height. So the height comes from where your grid point is, all the way up to where the function is, and then you draw over the width of the interval and back down. And that's how you get your rectangle. So in each of these, I'm using the leftmost point of all of my grid points. For the right-hand Riemann sum, as you guessed it, I'm using the right-hand point. So my xk star is going to be equal to my right-hand grid point, and I go up to the function, over to the left, and back down, and that's how I create my rectangle. Now the midpoint Riemann sum is, as you can probably guess, the most accurate of all of them because we don't get what we get in overestimate and underestimate kind of match up with one another. But I pick the midpoint of my subinterval, so if my subinterval goes here to here, I pick the midpoint, draw up until I hit my graph, then over both to the left and right, and I create my rectangle that way. So that's the left, right, and midpoint Riemann sums. So let's work on an example really quick. Let R be the region bounded by the graph of f of x equals 3 times the square root of x and the x-axis between x equals 4 and x equals 16. Approximate the area of R using a left Riemann sum with n equals 6 subintervals. So here I have pre-drawn, because the square root function times 3 is a pretty meaty function to try and draw on my own, but we're going to do it all together. So the first thing we want to do is determine the width of our subintervals. B is 16 minus A is 4 all over 6, which is the number of subintervals I want. 16 minus 4 is 12, divided by 6 is 2. So my delta x equals 2. Now I go ahead and I set x1 star equal to 4, x2 star equal to 6, x3 star equal to 8, x4 star equal to 10, x5 star equal to 12, and x6 star equal to 14. Just like I have here on my graph, I'm using the leftmost endpoints. And now all I do is I go f of x1 star times delta x plus dot 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 all the way up to f x6 star times delta x. So in longhand, I get 3 square root of 4 times 2 plus 3 square root of 6 times 2 plus 3 square root of 8 times 2 plus 3 square root of 10 times 2 plus 3 square root of 12 times 2 plus 3 square root of 14 times 2, and all of that equals about 105. So the question here is, does the approximation we have overestimate or underestimate the actual area under the curve? And if I zoom in really far, I can see that nowhere do I have any part of a rectangle above my curve. So it definitely doesn't overestimate. But here I've got a little area left behind, a little area left behind, again and again and again for each of my rectangles. It's not a perfect fit. It doesn't fit my curve perfectly. So there's something that my rectangles aren't capturing, which means that this is going to be an underestimate. So it's safe to say that the actual area under the curve is greater than 105. Now we're going to do the exact same thing, but we're going to use a right-hand Riemann sum. And it looks pretty much the same, but we get 3 times root 6 times 2, 3 times root 8 times 2, 3 times root 10 times 2, 3 times root 12 times 2, 3 root 14 times 2, 3 root 16 times 2. And all of that works out to be about 117.876. But if we zoom in really close, we see that while we have nothing left over underneath our graph, we definitely have more than we bargained for above our graph. So this is going to be an overestimate. So it's safe to say that the area under the curve is greater than 105, but less than 117. So finally, we're going to use a midpoint Riemann sum with n equals 6. And we're setting this up exactly as we did the last time. Except now we're using midpoints. So 3 root 5 times 2, 3 root 7 times 2, 3 root 9 times 2, 3 root 11 times 2, 3 root 13 times 2, 3 root 15 times 2. And you may wonder, Emily, where am I getting these numbers? And it's because when I divide my section into partitions, 4 to 6, 6 to 8, on and on and on, my midpoints are 5, 7, 9, 11, 13, and 15. So those are exactly the numbers that I'm plugging into my function and then multiplying it by my delta x, which is 2. So when that all gets worked out, oh my goodness. When that all gets worked out, we get a number approximately equal to 112. That number is less than 117 and greater than 105, so we can say we're probably a lot closer to the answer than we were when we used a left or a right-hand Riemann sum. So that's just a practical way of showing you that midpoint Riemann sums are usually your best bet if you're looking at something and you're like, which one should I use? Now, it's also possible to find Riemann sums from tables. So here we're going to estimate the area A under the graph of f on the interval 0 to 2 using left and right Riemann sums with n equals 4, where f is continuous but known only at the points given in the table. So here I'm going to makeshift draw my little intervals, and we're going to do the left one first. So left means I have 0, 0.5, 1.0, and 1.5. And then I'm going to multiply them by my width, which is delta x, which is 0.5. So for my first one, it should be f of 0 times delta x plus f of 0.5 times delta x plus f of 1.0 times delta x plus f of 1.5 times delta x. F of 0 is 1 times 0.5 plus f of half is 3 times 0.5 plus f of 1, which is 4.5, times 0.5, plus finally f of 1.5, which is 5.5, times 0.5. I'm sorry that's getting a little messy, but all of that works out to equal 7.0. Now we can do the exact same thing for the right hand. And all of that is going to equal 9.5. I trust that you can do the algebra to get to that answer. So with only 5 function values, these estimates of the area are necessarily crude, and better estimates are obtained by using more subintervals, which corresponds to more function values. So if we knew what was going on at, say, x equals 0.25, x equals 0.75, on and on and on, we'd be able to get a better approximation of what's going on under the curve. So as you can see, and you probably noticed that I'm getting lazier and lazier as each one of these examples goes on, but working with Riemann sums becomes cumbersome as the number of subintervals increases. It was pretty easy when we used just 2 subintervals, but once we got to 8, and once you get to 16 or even 50 or 64 or something like that, it's going to be a real pain in the butt to do all that math. Therefore, we're going to pause for a moment and introduce a new notation that simplifies our work. And this notation is called sigma notation. And maybe you've seen this before, maybe you've not seen this before, but we use the Greek capital sigma to express sums in a compact way. For example, we could write 1 plus 2 plus 3 all the way up to plus 10, or we could represent it in sigma notation as sigma from k equals 1 to 10 of k. The symbol sigma stands for sum, while the index k takes on all integer values from the lower limit, k equals 1, to the upper limit, k equals 10. The expression that immediately follows the sigma is called the summand and is evaluated for each value of k, and the resulting values are summed. So let's use a few examples. So what I have here is sum from k equals 1 to 99 of k. So when k equals 1, I write down 1, plus k equals 2 is 2, plus k equals 3 is 3, plus all the way to k equals 99. And that is altogether going to equal 4,950. And later on, I'll show you a trick on how to get a number like that, because I'm not going to sit here and add 99 plus 98 plus 97 all the way down to plus 1 to get what I wanted. That's just insane. I'm not going to do it. Now, this top number doesn't actually have to be a number. It can just be the letter n, and that just tells us that it stands in for a number. I can also square what's going on, and I can start from k equals 0. So when I do that, I go, when k equals 0, I have k squared, which is 0 squared, plus 1 squared for k equals 1, plus k equals 2 is 2 squared, plus k equals 3 is 3 squared. All of that added together is 14. I can make something a little bit more complicated, like 2 times k plus the value 1. When I go from k equals 1 to 4, that equals 24. And then finally, I can even start from -1. I can start really from any number I like. It doesn't have to be 1 or 0 or anything like that. It's just whatever happens to be convenient. And I can combine multiple representations of k. So here I've got k squared plus k. So every time you see a k, when k equals -1, you just plug in -1. And then you add that to the next term, which is when k equals -1 plus 1, which is 0. So we've got our -1 term, our 0 term, our 1 term, and our 2 term. And all of that sums to equal 8. Now, the k on the inside of my summand is actually a dummy variable, which means that I could use any letter I like. Most often you see k, l, m, n, p used, I and j also used. But you can use any letter you like. It doesn't have to be a k. So go ahead and pick your favorite letter. We can factor multiplicative constants out of a sum. That is, if I've got c times ak in my sum, I can have c times the result of my sum of all the ak's. We can also split a sum into two sums. So if I've got the sum of AK terms plus BK terms, I can split that into the sum of my AK terms plus the sum of my BK terms. That's always allowed. And then here's that thing I mentioned earlier. So if I have a sum from k equals 1 to n of just some constant value c, I'm adding that c value up n many times, which is the same as multiplying it by n. So the result of that summation is naturally c times n, where the n comes from right here. Now, what if I just have k on the inside? Then my result is n, same n as before, times n plus 1 all over 2. If I do k squared, my result is n times n plus 1 times 2n plus 1, all over 6. And if I've got k cubed, my result is n squared plus n plus 1, or times n plus 1 squared, all over 4. So these are good to have handy, and really you just have to memorize these, but they're going to come in really handy when you're working with summations. So suppose f is defined on a closed interval a to b, which is divided into n many subintervals of equal length, delta x. If xk star is a point in the kth subinterval, xk minus 1 to xk, for k equals 1, 2, all the way to n, then the Riemann sum for f on a to b is the summation from k equals 1 to n of f of xk star times delta x. And in fact, because delta x doesn't depend on k, we can pull it out. It's a constant multiple. We can just pull it out. And 3 cases arise in practice. So the left Riemann sum, our xk star is equal to a plus k minus 1 times delta x. Our right Riemann sum is xk star equals a times k times delta plus a times k, Our xk star is a plus k times delta x. And our midpoint Riemann sum is xk star equals a plus k minus 1/2 times delta x. So here I want to evaluate the left, right, and midpoint Riemann sums for f of x equals x cubed plus 1 between a equals 0 and b equals 2 using n equals 50 subintervals. And then I want to make a conjecture about the exact area of the region under the curve. So the first thing I'm going to do is calculate delta x. Delta x equals b minus a over n equals 2 minus 0 over 50 equals 0.04. And since we're doing the left Riemann sum first, my xk star is equal to a plus k minus 1 times delta x. Well, my a is 0, so I just get k minus 1 times 0.04, which means I get 0.04 times k minus 0.04. And I'm going to plug that into my function every time I get a chance. So my summation looks a little like this. K equals 1 to 50 f of 0.04 times k minus 0.04 times delta x, which is 0.04. Now, I can even make this a little bit simpler for myself and plug in furthermore when f of x is x cubed plus 1. So I really have 0.04k minus 0.04 cubed plus 1, and all of this times my delta x of 0.04. I wonder if I have, yes I do. So I'm going to copy this to my next slide. Oh, that erased it. Good job, Emily. Copy. Paste here on my next slide. So the first thing I know I can do is, well, I can pull this 0.04 out of my summation. So I really have 0.04 times summation from k equals 1 to 50 of 0.04 k minus 0.04 cubed plus 1. And now this is simply the art of breaking it into two separate summations. So I get 0.04 summation 0.04 k minus 0.04 cubed plus 0.04 summation 1 k equals 1 to 50, k equals 1 to 50. And you can see where this is going.